So welcome to Breaking Science. This is the Renewable Energy Week. And thought instead of going super in-depth into the exact science of a particular type of energy, I would just do a quick primer on just what is renewable energy. What are we found it, thank you. Well, we bought one, actually. So what is renewable energy? What are people talking about when they say renewable energy? So the first step towards figuring that out is figuring out what is energy. Does anybody know what the scientific definition, Jim, be quiet, of energy is? Scientifically what energy is? Yeah, well, now you're getting into the numbers, yes. It is, I think, but energy is the ability to do work. Energy is the ability to do things. So there's a lot of different kinds of energy. So up here I've got 4 different important kinds of energy for this. And so up top left we've got, have an idea what that is? Yep, mechanical energy. So mechanical energy is the energy of things moving. Things colliding with each other, things being pulled by gravity, things swinging. That is mechanical energy. Kinetic energy is a type of mechanical energy, as is potential, which goes with it. So that's mechanical. There's 3 others. Who's got?
Thermal?
Yes, thermal. Thermal energy. The very, well, I don't know what is burning there. Probably propane. Thermal energy is the energy of heat, of things moving, of molecules moving, molecules vibrating. That gives things an energy to them that you can feel. It can radiate off through space in the form of radiation, or move through a gas at convection, or directly as conduction. So that's the most basic form of energy there is, basically. The most simple is thermal energy. There's 2 more. There's one easy one and one kind of tricky one. Electrical, yes. Electromagnetic energy. So electrical is half of electromagnetic energy. It was figured out quite a while ago by some very clever people that electricity, if I could say it properly, and magnetism are sort of 2 sides of the same coin. You can't really have one without the other. If you have electrical charges moving, you're going to get a magnetic field. If you move a magnetic field, you're going to get electrical charges moving around. So the last one up there is a little tricky. Plasma is a type of matter, but it is fire is a plasma. It's an energized gas. Jim, do you? Chemical energy, yes. So chemical energy is the energy that is bound up inside molecules and atoms when they bond together and the bonds break. So the simplest one is like your baking soda vinegar reaction. When you mix those 2 together, they release carbon dioxide gas, they release some heat, and you don't have baking soda and vinegar anymore. They've changed. So that's the energy involved in chemical changes. And those 4 are very important to how we get our power in our house. So where does the energy in your house actually come from? Do you want to plug in your phone or watch TV or use your computer? Install. But where is it in your house? What's the installation? What is it? You know what it looks like?
Plug?
Yeah. You got the wall outlets. So everyone just sort of sees, you got a wall outlet, you plug it in, everything's great. But where does the wall outlet actually get its power from? Through the power lines, yes. Yes, through the power lines. And hello. Hi.
Is this audience?
Yes. Yes. Yep. We're a little, nothing too complicated. We're still at the beginning. So do you know where the power lines get their energy from? Yes. Is that what you were going to say?
No.
I stole it from under you. Yes. The energy in your house eventually all goes back to a power plant. So what is a power plant? A power plant is basically an electricity factory. So this is one, I believe, in Germany. It's quite new, quite clean, very modern. So how does a power plant work? What is going on in that building? And there are several different kinds of power plants. We're going to go over different kinds and sort of describe how they work and what the breakdown is. So this is an example coal power plant. This is a very simple one. Oil plants are similar, natural gas plants are similar. They all sort of start with a fuel over here. So in this case we're using coal. And the way that you get power out of coal itself is a chemical, or a set of chemicals. Everything's made out of chemicals. All of matter is made up of things called chemicals. So if you ever hear anything about your food has chemicals in it, of course it does. Everything does. And what we do with this is a special chemical reaction called combustion. So if you've ever been camping and you're cold and you need some light out, this is a very good way to get some. What you've got here, this is a hydrocarbon, which is a molecule of hydrogen and carbon. It's pretty simple. This is about the simplest thing that you can burn. And you combine that with oxygen, and you'll get carbon dioxide and water vapor. If you've ever seen wood outside, you know that you put wood on the ground, it's not going to burst into flames. You have to get it hot first. So that's part of what goes on in here. You have to heat this up. And as long as you have heat, you have fuel, and you have oxygen, the fire's going to keep going. If you throw water on it, that takes away the heat. If you throw sand on it, then that blocks the oxygen. And if you run out of wood, then you run out of wood. So there's lots of different things that you can burn. It's not a challenge. You don't have to try it. But there's propane, which is in your gas grill. You've got methane, which is very similar. And this is cellulose. This is a sugar. So sugars are used by plants and animals to get energy from. Essentially, they even come with the reds. It comes with its own oxygen already in there. So it's very energy dense. It's easy to burn. It gets you a lot of power when you do burn it. So we've got over here, this kind of spoils it a little bit. So we've got the furnace here where we have a fire. And if you're trying to, hey there, sorry, we're a little, not too far in. Should still make sense. I missed the important parts at the beginning. What?
So you just said cellulose is really flammable.
Yes.
Because I have cellulose insulation in my house. Is that a bad idea?
Blown cellulose, it's a process.
Okay.
So this spoils it a little bit, but if you're going to try to make pasta, or you're going to make something on your stovetop, and you put a pot of water on a hot stove, what happens to the water? No. This is very, sorry, yeah, in case you missed the beginning, it's very back and forth. So yeah, audience participation is encouraged. Yes, and you say, what? It does, yes, it will boil. So what we're doing here is we are taking this chemical energy that's in the coal, and we are burning it, so now we have thermal energy. We've changed the kind of energy. You can't actually create or destroy energy. That's thermodynamics. You can just change what type it is. So we've gone from the chemical energy in the coal, and now we've got thermal energy over here. So we're going to boil that water that's in this, we're getting it from the river, and it is going to boil over here. Yeah, here we go. So this is a very smart man, Sir Charles Parsons, from back in 1884. He invented the first steam turbine. Now what that is a set of, these are all little, they're almost like fans. You can kind of see them here. These all have just rows after rows of blades, and what they do is they boil the water, and when water boils, it turns into a gas. It takes up a lot more space. So if you have a small vessel that can only hold so much material, and you add more stuff, you add steam, which takes up more space, it's going to increase the pressure. So what they do is they take that pressure and they blow it across all of these fan blades. And this, it's actually moving, it's hard to see. But all of those wheels are going to spin, and they're going to move that central, is it called an axle? Yeah, central axle, that sounds good. Yes?
Does any water touch the turbines, or is it all
There probably is some condensation. I'm not sure exactly how hot they get the steam before they put it in there, but I think the idea is to have it cool down. Yes. So this over here, the condenser, that's where you're meant to cool the steam down. So that's where it turns back into water. So it shouldn't be getting too wet. It's all very hot. So what are we going to do with this spinning axle? So we initially had coal for chemical energy, burned that to get thermal energy. Now we're spinning this turbine to get the energy of moving things. Now it's mechanical. So now we have stuff moving, we've got this turbine spinning. This man, Michael Faraday, you may have heard of him. If you've been to the Museum of Science, their lightning shows, they talk about him during that. He's very important to the lightning show. He discovered, back in 1831, that if you spin a copper disc in between, these are magnets, there's magnets in here, and if you spin that copper disc, you actually get electricity moving through this wire, because I mentioned this in the beginning, electromagnetic energy, if you have moving magnets, you're going to get electricity. If you have moving electricity, you're going to get a magnetic field. So he found out that you could actually get one from the other. So he was able to take mechanical energy of a spinning disk and turn it into electromagnetic energy, which is very useful. Now we've sort of made better versions of Faraday disks. His was maybe enough to power like a Christmas light for not very long. They weren't producing a lot of electricity back then. Now we have to provide power for people's houses, and that's a lot more effort. So this is, I believe, called an alternator. The newer ones actually have a new name. There's one in your car if you have a combustion engine car. If you have an electric, you do not have an alternator. And so that's the breakdown over here. We got chemical to thermal to mechanical to electrical. There's one other kind of plant that sort of operates mostly the same way once you get past the beginning, and that is the nuclear plant. There's one up in New Hampshire, not that far, and they work very similarly. So you see, we still have the generator, we still have the turbine, we have a boiler over here, boiling water, it comes around. The only difference is how we get heat out of the fuel, which is uranium for the most part. So who's heard the word isotope before? Oh, excellent, I have less work to do.
I'm sure I have, but I probably forgot.
Yeah, it's one of those things that it doesn't come up too often. So the number of protons in an element determines what element it is. If you have 92 protons, it's always going to be uranium. There are electrons flying around the outside. They don't determine what element it is, they determine what ion it is. We're not using ions. What we care about is the isotope, which is how many neutrons there are. Neutrons are neutrally charged. So protons are positive, electrons are negative, neutrons are neutral. That doesn't mean they have no charge. They have a positive and a negative, and then they kind of don't really know which way to go, because they've had some of each. So this number up here, the 238, is just 92 plus 146. So that's what this is. This one, uranium-235, has fewer neutrons, and it is lighter and less stable, which means that if you smack it with another neutron, it turns into uranium-236, which basically explodes immediately. It's extremely unstable. It fractures into a couple different pairs of atoms, so all that has to happen is that this number down here, for krypton is 36, for barium it's 56. Those just have to add up to 92. We don't care what they're. It's like if you try to break a cookie in half, you're not quite sure where it's going to break. So there's a couple different options. And it releases a lot of energy as heat. Everything gets very hot when this happens. And you get more extra neutrons that fly out and hit other uranium atoms. So that's called a chain reaction. That's a phrase that you will hear about other things, but that's what originally a chain reaction was. So the neutrons fly out, hit more uranium atoms, then more of them fly out, and they use control rods that block the neutrons so that they can keep things under control where they want it. They don't have any disasters. This is just sort of to show you, there are all different combinations you can get. of different elements that add up to 92. So that's all down here, these add up to 92. And you get sort of these groups. You're never quite sure which one you're going to get, but it's one of those. Has anyone heard of the term half-life? And do not say the video game.
Yeah.
Yes. So that's a thing. Half-life is a lot of the reason we care about the dangerousness of spent nuclear fuel. So when we burn that uranium and we get all those other elements out of it, it's still radioactive. It's very dangerous. It's toxic. You can't even really go near it. You don't have to touch it even. It's just going near it is a bad idea. And half-life is why it is so dangerous. Half-life is the amount of time it takes for half of your radioactive stuff to decay into something less radioactive. So from 1 to half, half to a quarter, quarter to eighth, it's the same time period. So you never quite get to 0, but it gets there pretty safe eventually. The reason those are concerns sometimes, and I'm not going to go into all of this, but some of these examples here you can see, so uranium-238 has a half-life of 4.5 billion years, which that's a little bit old. So of all the uranium that existed when the Earth formed, half of it is gone. It's decayed into, first it goes to thorium. Thorium, its half-life is 25 days. So there's a big mismatch there. So you get these elements sort of decay along this chain, and they're very, very different. So you have 4.5 billion years, 22 years, 1,600 years, 27 minutes for some, 1/1000th of a second for polonium-214. It barely exists for even an instant, and then it immediately transitions away. So the problem is that some of these things hang around for a very long time, and they stay dangerous for a very long time.
Do you want to take a picture?
No. Go ahead. So what happens, the way this works is, you can see these alpha and beta symbols. That means that if there's an alpha, that's alpha radiation, which is the atom just threw away 2 of its protons and 2 of its neutrons. So it changes elements. So it goes from uranium to thorium because we have a different number of protons now. So because we don't have 92 protons, we're not uranium. When you see beta, that means that the atom has thrown away an electron. But it didn't have an extra electron. That's a neutron becoming a proton. So you've gained a proton, so you change elements again. So you can actually go from uranium back to uranium. It's a different kind of uranium. So there's, I think lead is on here at least twice. Lead is on here 3 times. Polonium's on here at least twice. So you get repeats of some of these things. And so that's just what this is. It's a little bit confusing. But. So what do we mean when we say renewable? Oh, I'm sorry, yeah, go ahead.
Remember something that 3 times different
Yes.
half-lives?
Yes, different half-lives because they have a different isotope. See, this is lead-214. That is one isotope of lead. Yes?
And after like the uranium is gone, like was the everything back?
That's part of what we mean about renewable. So the uranium is not coming back.
Oh.
We don't really have a way to get the uranium back. Yeah, they come back in the way that the uranium was created in the first place was a star exploding. And we don't have any exploding stars on Earth, really. It would be kind of hard to keep that all in place. So as far as we know, there's no good way to get that uranium back. So when we talk about renewable energy, that's sort of what we're getting at. There's no way to get that uranium back. The uranium is not being created as fast as we're using it. Yeah.
Can I ask one more question about the previous slide?
Yep.
So it's throwing off protons? Is that
yeah, so the alpha one is 2 protons and 2 neutrons. So you see it loses 4 atomic weight. So it loses 4 particles, basically.
I had a question about the efficiency of some of these plants, because you're going from chemical to thermal to mechanical to electric, so you must have like a loss of efficiency.
Yes, so that is important. I will actually touch on that later.
Okay.
But every time you switch forms, you are going to lose a bit. anytime you do anything, really, anytime you use energy, yeah, anytime you do anything, you're going to get some heat. So if if I just, did that, the floor is a little bit warmer now than it was. It's not much, but anytime you do anything, you're going to lose some energy to heat. And also when you switch types, you can lose a bit of efficiency as well. So that is important to think about. Yeah.
I just had a follow-up.
Oh, I'm sorry.
No worries. If you're losing a proton, and the element is defined by the number of protons, how does it go back to being the same element?
Oh, so yeah. So that's it took me a little while to get that as well. So the alpha particle is actually a helium, I believe it's a helium atom. It's 2 protons, 2 neutrons. It just zips off very quickly, and now that atom is, if it moves down, becomes thorium because it changed the number of protons. So the opposite sort of happens. It gains a proton by a neutron turning into one. And the electron that was left over just goes away. Alpha particles, I think, are they're easiest to block, I think. Alpha radiation, I think, is blocked by a piece of paper. Beta, I think you need clothing will block it. It's not that deadly. Gamma radiation is the kind you have to be afraid of. None of these do gamma. That's not in this. I think they do make like little diagrams like this that show you what type you're getting. Your gamma is just a giant burst of energy that is not friendly to anything. Will not become the Hulk if you get hit with gamma rays. You'll just be very upset. Oh yes, renewable energy. Renewable in this case. So I'll explain it a bit with as an example for coal. This is how coal is made. So if you have a swamp with lots and lots of wildlife, there's lots of trees, lots of vegetation, and a lot of water. Things that die just sort of fall into the water and pile up and decay to a point, and more trees come in, and more trees fall down, and more grass grows, and more grass falls down. There's a lot going on in wetlands. They're very active. There's a couple national parks, not national parks, state parks, up north in the North Shore that you can go to see this. It's actually really nice. You can actually get this stuff called peat when that piles up enough. They use it in their fireplace in Ireland, if you've ever been. Very distinctive smell. So if you bury peat deep enough and wait long enough, you need a lot of pressure and a lot of heat that you only get from being deep underground. You eventually get lignite, which is a rock. It is actually stone. It's that peat has been compressed enough that you have actual rock now. And if you wait more time and give more pressure and more heat, you get coal. The trick is this time bit. So if you were going to you decide you want cookies. I want cookies tonight at 7. I'm going to have to start making cookies at probably 6 because I have to mix everything up. I got to warm up the oven. I got to put everything in the oven and then wait for them to be done. It takes some time. So if you want cookies now, start an hour ago. If you want coal now, you would have to start about 250 million years ago. So if you did not start your coal a long time ago, you are not having new coal today. So it takes a long time to get this stuff. Renewable just means we're generating it faster than we are able to use it up. So if you have a rain barrel in your backyard and you only really use about half of it every time it rains and you're topping it up every time, it's not telling you need to use more water, but if you just watch what you're doing and you're careful and you don't go crazy with it, you can probably just keep using that water and not have to worry about where you're going to get more water. So if we wanted to have something, we want to use the old model of power plant that we had where we were burning coal. Is there anything anyone could think of that we could burn instead of coal? It would be a little bit more renewable. Oil takes a long time too. Oil is also a fossil fuel, so oil, natural gas, and coal are they take a very long time.
Probably wood.
Wood is a good one.
Water.
Yes. Water doesn't
Oh.
burn.
Oh, sorry.
No. You were looking at water. I can see why you would say water. So we refer to wood in this case as biomass. This would be a biomass plant. And what they're able to do is we can gather up all kinds of just extra garbage plant stuff that we're not going to use. So at farms, they can say, oh, we have extra corn stalks, we have corn cobs, we have all these things that we don't need, we stick them in a bag, and you ship them off to a plant. If you ever had to rake leaves or mow the lawn, or do the yard work, you got to trim the bushes, now you got sticks and everything, and you just put them in a bag and the town takes them away. They can take it to a biomass facility. If you have a wood shop, you're going to have a lot of sawdust and wood shavings, so you can use those, and they compress them into these little pellets that you can burn more easily, and you put them in a stove. And a lot of people will say, well, hey, if you're burning stuff, you know, you're going to get carbon dioxide, and that's what causes global warming, right? Yes, but the thing is that when we are burning fossil fuels, which are coal, oil, natural gas, those were buried, those were out of the picture. They were way, way underground, and they weren't moving around in the air. They were completely out of the picture. Trees are actually made of air, which the first time someone said that to me, it blew my mind a little bit, but trees do photosynthesis in their leaves. That's what the green color is for. It's from chlorophyll, which plants use to take carbon dioxide from the air, water from rain from the ground, and sunlight, and they create tree out of that. Wood is just solid air, which is kind of crazy, but that's how it works. So when you burn a tree, or you burn what's left of it, say a tree falls down in your town after a storm and they put it through the chipper, and now you just have, they're just going to throw it away. So what we want to do is we want to take that and use it before it just rots, because that carbon is going to go back in the air anyway when the tree rots. So we're sort of thinking, well, hey, could we just use what's already here? This energy is just waiting to be used and nobody's using it, so let's give that wood a detour instead of having it get eaten by fungi or bacteria or termites. So we're going to try to use it when it's already there. And a plant like this is not going to power a giant city. You know, you're not going to power a whole state with one of these. This could be like a municipal plant in your town. You could just have this, everyone brings their yard waste, dude with the wood shop brings in his sawdust. And we're sort of looking at ways to take a little bit from a lot of different places, is what we're looking to do in the future with energy. So what he said before, he mentioned that when you switch types of energy, you're kind of losing some efficiency there. When you go from burning something to using that heat to boil water, you know, what if we didn't have to ship fuel? What if we, you know, didn't have to pay the driver of the truck? What if we didn't have to mine anything or gather anything? Does anyone know another good way to just get heat? Anyone think of anything? Solar thermal is a thing. Yes. So these are really cool looking. Cool new futuristic looking source of power. And so who's been to the beach this year? Yeah. So what happens when you go to the beach, you sit under the umbrella, you're having a great day, and then, you know, it gets to be late, and you go back to your car that's been sitting in the sun all day, and you open the door, and then you want to die because it's like 150 degrees in there. That's how we get heat into a solar thermal plant. It is essentially, the reason this happens is because of the way glass works. Sunlight can get through glass, and it heats things up inside your car, your seat, your dashboard, your steering wheel. The heat can't get back out because your car is pretty sealed. That's why leaving your windows open a little bit helps, because that heat can kind of escape. But you can see within an hour, it gets to be ridiculous. That's why you can't leave kids or pets, or, I mean, if you went to the store and bought a really nice plant and then went shopping at the supermarket, you're probably down a plant. That level of heat is not good for anything, but it is good for boiling water. So what they do in a solar thermal plant is they aim all these mirrors. These are called heliostats, which is
That happens when like a bug's in the water, and then that's why it comes out
Don't, yeah, it's not nice to drink water that's been sitting in your car. It's nothing about that is good. So heliostat just means, helio means sun, stat means stay. So what that mirror does is it just makes sure, with a little computer in it, that it is always aiming the sun's reflection at that tower. So there's a whole field of these. Just all of those are all pointing the sun directly at that central tower right there. And that gets very, very hot. You can't go up there while these mirrors are all aimed there. If you threw a baseball, you just leave it burst in flames. That's not a good thing to do with a baseball. So what they do is they aim all those mirrors up there. It gets very, very hot. And what they could have done was put a boiler up there because it's hot. You know, you can just boil your water. And then someone very clever said, well, hey, what happens at night? You know, what are we going to do at night? There's no sun. And they were like, oh, right. We spent all this time and money building this big fancy thing. Seems like a waste. So some chemists came up with, let's use molten salt. So this is a mixture of a few different kinds of salts. I think there's potassium, there's sodium in there. These stay liquid at very high temperatures. They don't like to boil. So when you put water up and you get it up to 100 degrees Celsius, it'll boil. This salt will not boil. I think it can get up to thousands of degrees in that tower before this salt still does not boil. So they send this cold salt up. It gets very, very hot. It comes back down, and they hold on to it here until they need it. And that salt will stay hot all night. It holds on to heat very, very well. So they use it all through the night to power their steam generator, which drives the turbine, drives the generator, you have electricity. It's the same sort of idea. So we're still using that boil water, drive a turbine, get power that way. These are really cool looking, and yes?
If energy lost from the efficiency of shifting between different forms, why is it necessary to have so many different forms?
It's just sort of how things developed. Like, it was less high tech to figure out how to burn coal. Like, that was an easy step. Everyone knew you could burn coal or whatever you're burning. You get heat from it. You can feel the heat from the fire. And they sort of discovered the other steps later as they were going. Like, somebody realized, hey, I can spin, Michael Faraday realized I can spin this disc and get power. And the people were like, well, how could we spin the disc without us having to do it? Because you used to have to do it by hand. Like, he turned a crank. And he was turning a crank for maybe enough power to power a Christmas light. Just to sit there for hours, not really doing anything. So they were looking for, how do we do this without us having to do it? So that's how they sort of came up with those steps. It wasn't all designed all at once. It's sort of, the engineering word for it is a kludge, is when you're sort of like, well, I have to do this thing, and I've got, it's kind of like MacGyvering something. You know, if you know what that means, to just throw together something with what you have. That's kind of how that happened. So with solar thermal, you kind of have to have a big, wide, flat area to put it in. You don't want trees in there because they just block the sunlight. You probably want a flat horizon so that you don't have mountains blocking your view of the sun, because it needs sun on all those mirrors to work. So there are places you can put it, but there are definitely places that are better to put it. I believe this one might be in California. I believe there's one in California. I think they're looking at Arizona. There's a lot of desert. So that's solar thermal. What's another way? So who's been to, I think you have, who's been to like Yellowstone National Park or Iceland? Yeah, I know you have. You have? All right, so I'm very jealous of you got to go. I did not. So who knows what's going on in those places? Yes. So geothermal is essentially the crust of the earth is thinner where you are looking at these things like Yellowstone or in Iceland, in Japan. There's a layer of solid rock on the surface of the earth, and then as you go further enough down, you get to very hot liquid rock. And what's happening in these places is that the heat is closer to the surface. The lava and magma, if it gets to the surface, you get volcanoes. So places like Hawaii, or Iceland again, things like that. Italy, some in there. So you get these features that you don't really see anywhere else, and they're all caused by that heat from the surface, the center of the Earth. And that heat is not, you're not going to use it up. It's not limited. It's there. It is doing these things, so you can have different kinds of geological features, like based on where the water is next to this heat. But these things only happen where there is a big source of heat close to the surface. It's actually really, really easy to get power from this, because all you do is you put water in the ground and it comes back up and it is very hot. You skip a lot of the having to burn things, having to ship fuel. You just put the water in the floor, and now it's very hot. Drive your turbine, generate electricity, you're good to go. There are actually, there are a lot of these. You can see they're in a very sort of distinct region. This, if anyone's heard of it, is the Ring of Fire around the Pacific. There are a lot of volcanoes, a lot of geological activity. Iceland is a madhouse of geology. There's even some in Germany and Turkey in here. So this isn't power generation, but it's another, I'm sorry, yeah.
Do you know what prohibits people from using the geothermal energy deeper down? Like, why can't they?
Mostly cost.
Just cost.
If you are going to try to do it in a place where the magma is close to the surface, you're not going to have to dig nearly as far, because as you start to dig further, it gets really expensive.
Is it physically possible to?
You can dig very deep. You're never going to get to the mantle. Like, you're never going to get through the crust, because as you start to go down, the pressures just get so great that they destroy your tools. There's a super deep, I forget where it is, I think it's in Siberia somewhere, a very, very deep borehole where they just took this massive drill and kept pushing it down further. And the problem they had was eventually it got hot enough that the drill couldn't operate anymore. And it started to just catch because there was so much pressure that the rock was bending.
Would that heat down there be high enough?
It would. It would be very, yes, it would be very much hot enough. It's just an issue if it was very expensive to do that.
Yeah.
And if you're trying to get power economically and you're going to say, hey, I want to build this new power plant, and you tell them how much it costs, they're just going to say, okay, fine. It's very pricey to dig that deep in places that aren't really made for it. There are some things you can do at home now. If you have ever heard of a heat pump, they have geothermal heat pumps for your house that if you dig far enough down, it's about 68 degrees all the time. So it never changes, and yeah, Fahrenheit, just comfortable room temperature. It gets very different at different stages. It's just like it's 50 here, it's 60 here, it's 68. If you go to the right depth, you can get 68. That's the idea with this, is that you sort of, in the winter, you chill this fluid with the cold air in your house, send it down to the ground where it's warmer than it is in your house, and bring it back up and use that to warm the air a little bit. And heat pumps don't use much power at all, so that's a lot easier than trying to run an air conditioner or a heater. It works the opposite way in the summer because it's still 68 down here. You ship your 90-degree, hot, humid day air, use it to warm this fluid, bring it back up, and it's a nice 68. So one of the important things about renewable energy is sort of learning how to do more with less, how to be more efficient. And a heat pump is a lot easier to power than air conditioner and central air, central heating. It's still kind of pricey to dig down in the first place, but it's an option that we have. Well, spoilers. So, who knows what this is? Yes, so what we're doing here is, like you said, we're going to try to switch energy types fewer times. Instead of having to heat up steam to drive a turbine, we're just going to drive the turbine just by ourselves. So we can do that with the wind. The wind is always moving. It's never going to go away. As long as there is air on the planet, there's always going to be wind. And that happens because there are different temperatures in different places. When you have a nice bright sunny day, that's usually a high pressure system where air comes down and goes out from there, and it spirals around. And when you have an updraft in a storm, that's low pressure, and that sucks air in. You notice whenever you have a thunderstorm, it gets very windy. That's part of why. So these processes are always happening. All you really do is you stick a turbine on top of a pole. You just put a generator on top of a pole, put some propellers on there, and you're good to go. Wind blows, turns the turbine, you're all set. And you can get very small turbines. This is actually a vertical turbine. It doesn't fight gravity. It just goes around in a little circle the other way. And you can have big turbines. You can have small turbines. You can have one on your house. So the idea, again, is to sort of decentralize how we're generating power, sort of get a little bit over here, a little bit over there, and that sort of reduces the strain on the system, makes everything a little more robust, and it's sort of like everybody doing their part, working together, sort of thing. What else could we spin a turbine with instead of air? Yeah. So this is the most familiar version of this. This is a hydroelectric power plant. This is a dam. Some of them are very spectacular. It's essentially just a wall that blocks off a river, and they build up all that water behind it, and then that water goes through a tunnel and spins your turbine for you. And you can generate actually a lot of electricity that way. You do have to worry a bit about habitat destruction, because you saw there's this big lake here now that wasn't there before. You want to make sure you're not going to flood anything important. You want to make sure that fish have a way to get up the river, because that is a concern in some places. But again, you kind of have to build this where the power is. But rivers are always going to exist, and they're generating power whether you're there to capture it or not. There's other ways you can even have small turbines that work like wind turbines, are just in a river. And because water is so much heavier than air, it compresses with a lot more force, and this turbine doesn't need to spin very fast. It's not a boat propeller. This fish is not in danger at all. If he swam into the propeller, it would just sort of nudge him out to the side. So there's, we want to be careful of habitats and habitat destruction and danger to animals, and this is a lot safer than it looks. Get what's on this, so we'll chance it. Nope, we're good. So there are other ways that you can get power out of water. And aside from rivers, what's another very prominent way that you often see water moving around? Yes. So tidal power. Tidal power is indeed a thing. There are a lot of different ways that you can get it, but sort of the reason tides happen is because of the gravity of the moon. It pulls the water moves more than the Earth does, and you get a sort of bulge of water. And the moon is going to keep orbiting the Earth. That is going to keep happening for quite a while, as far as we know. In some places you can see that, I believe this Bay of Fundy is very, very prominent. There's a big difference between high tide and low tide. Mont Saint-Michel in France, very big difference between high tide and low tide. So what you can do is sort of gather that power as they build a mini dam. And when the tide comes in, it refills this segment, and you get power going that way. And then when the tide goes back out, it goes the other way. So you're able to sort of get power out of this both ways. These can get very expensive if you build a big one, so a lot of times you probably want to build a small one off to the side, so you have to worry a little less about the huge construction costs that you can rack up if you're trying to build a very large one. If anyone's seen like the Three Gorges Dam in China, it's very expensive to build large projects like that, so you probably want to stay small with these, but that's part of what we're trying to do with energy in the future anyway, a bit more, is to decentralize things so you're not going all from one plant. Whoops. Spoilers again. Then there's wave power. There are a lot of different ways to do this. So again, the ocean is always going to have waves. That is how water in large bodies works. This one is, I believe it's called a polamis. So as these segments move around and snake back and forth, they generate power at the anchor points, at the intersections. So as long as there's waves going past this, it's going to be moving, it's going to drift around, and it's going to generate some power. You could also go with a buoy. So if you've ever had to start a gas-powered lawnmower where you pull the stupid cord and then your lawnmower doesn't start, that's kind of how that works. Every time the buoy goes up, it pulls on the cord, and when it goes back down, it lets it in. It pulls it and pulls it and lets it back in. There are also models that use a little float that will move relative to the buoy, so that that generates a little bit of electricity. And you can have as many of these as you want. You just have to, watch out and make sure you're not going to have boats getting tangled in them, things like that. And I believe this one was called an oyster or a clamshell or something like that. But the idea is that when the waves go by, that float at the end gets shoved back and forth, and you're generating power in here. And I think they show these little cables, but yep, there it is. You want to be careful with things like this, that you're not making a lot of noise that's going to disturb whales or dolphins. And if you're going to have a lot of barnacles or mussels growing on it, you're going to want to have to think about how that's going to affect the ecosystem. But there's a lot of different ways to sort of go about this. Yeah, spoiled again. So, we were talking about not having to switch forms of electricity, forms of energy over and over again. We're still doing mechanical into electrical. So this is a good way to not do any of that. Nothing moves, nothing changes, there's no chemical reactions, there's no water being pumped around. This is just, here is electricity because the sun is out. So the way a solar cell works is that you have two layers of silicon wafer. One has more positive charge, one has more negative charge. And when the sun comes out and throws photons, photons are the particles that make up light. When a photon comes down, it'll smack into an electron, and the electron will get knocked into the zone it doesn't really want to be in. And it says, okay, so how do I get back to where I was? So we give it a path over here. So the electron just sort of wanders around and goes through, goes back, and now we have electrons moving, which is how we get electricity. And that happens every time a photon hits one of the electrons. It winds up where it doesn't want to be, it goes back through the path that we gave it, and we get a little bit of electricity out of it. It's only a little. An individual solar cell does not generate a lot of electricity. You can sometimes buy little kits that'll have them for if you're going camping and want to charge your phone while you're out in the wilderness. But each individual cell is not going to give you much, so we put them together into solar panels. And these are what you see on people's houses, sometimes in fields, things like that. You sort of just throw more at the problem. If one only gets you a little bit, you just make more of them. And the cost associated with making solar cells has gone way down. So we're a lot more able to make these big solar farms that can provide a lot of power all the time. And there is maintenance. You do have to clean them so they don't get too dusty. And they do eventually wear out, I think, but there's new technology that's making that a little bit less of a problem. So that's a really good way to just go straight from sunlight to energy and not have to worry about shipping fuel around and doing all that kind of stuff. So what does the future hold? Where are we going? Some things, some ideas take off. That was horrible, I apologize. Some ideas work, some ideas don't, but you never know which one they're going to be, so you gotta make the effort. This one is actually pretty cool. I believe this is a company called Alteros. They're making a kite blimp wind turbine that just sort of sits up there and spins its turbine. And if it's very windy, you can take it down and not have to worry. It's instead of a kite cord, it's got a power cable. And if the turbine breaks, and this is key, if the turbine breaks, you just bring the whole thing back down and fix it. I work up in Gloucester, and we have this really big, awesome wind turbine, and it's broken, and it hasn't worked for like a year. They spent all this time and money, exactly, and all this time and money building this big, awesome source of power, and now it's not generating anything. They've now started to fix it. I think they finally got the crane that's big enough. So that is a huge plus for this. This thing is very, very low maintenance. Even if it completely breaks, it's very simple. So that's one thing we can do. This is, I believe this was in France. This is halfway between a science exhibit and an art installation. There are these little vertical green plastic wind turbines, very light, they spin very slowly, and they're on this sort of model tree, and it's nice to look at. So it's sort of this halfway point between a sculpture and a power generator, and it's just some kind of fun way to do things. I would put one of these in my yard if I could do that, but it's sort of fun little things that towns or cities can do to sort of get some attention and also maybe power some of, like the lights in a park. If you have LEDs, are very low on power usage, you could conceivably have these power those. These power those. There has been, I don't think anyone's doing it yet because it is very high cost, but there have been ideas to put solar power stations in space. To just have solar panels upon solar panels on a satellite that stays up in space, in the sun all the time. There's no dust, there's no clouds, there's no storms, there's nothing. It's just, there's no night. It's just always staying in the sunlight, and it would theoretically beam down maybe a microwave or something like that to a receiver that would be able to convert that into actual usable electricity. Would probably have to switch which receiver it's going to as the Earth goes by under it, but it's always up there and it's always getting power. So that's an option. That's there. Algae, surprisingly. Algae has been conscripted. Algae is very, very small plants. They have genetically engineered some kinds of algae to produce oil. Not like black crude oil, but more like olive oil or vegetable oil that you could then extract and burn if you wanted to. And they have these reactors that sit out in the sun, because algae needs sun, algae needs air. And so you could theoretically be cleaning out the atmosphere with some of the carbon dioxide that we have that we don't really need quite so much of, and be able to turn that into a usable fuel. It's still very early on with that technology, but it's something that people are pursuing. I believe the next one, so, yep. So who saw Spider-Man 2 back in the day? This was like, I was just the right age for this to be the coolest thing ever. Dr. Octopus in this movie was attempting to make a fusion reactor and a fusion generator with a self-sustaining fusion reaction in it. Probably, if you were really to make one, would not look quite like that. It would look more like this. So when you mentioned plasma earlier, plasma is gas that's so hot that the atoms don't really work anymore and the electrons are kind of just all over the place. It's a charged gas, so it responds to magnetic fields, and it's very, very hot. The sun is made of plasma, and fire is plasma, a lot of things that you're not quite sure what state of matter that would be, solid, liquid, or gas. It's actually, sometimes it's plasma. So the way the sun gets its energy is it crashes two hydrogen atoms into each other. Atoms don't like to touch, atoms don't like to go anywhere near each other, they're mostly empty space, so to squeeze them together like that, you need a lot of pressure and a lot of heat to get the energy required to do that. But when that happens, it lets out an absolutely obscene amount of energy. Because if anyone's heard Einstein's E = mc squared, if you convert matter into energy, even a tiny little bit of matter gives you a lot of energy. So that's what's going on in the sun. The sun is just a giant ball of explosions. On Earth, we would probably need to use deuterium and tritium, which are isotopes, like we were talking about earlier. They fuse more easily, is the main reason we want to use them, because we can't really build a sun. That's a little much. So that's how fusion reactions work. On Earth, we would squash the deuterium and tritium together and capture that energy. This is what the inside of the reactors they've built look like. Tokamak? It's called?
Yeah.
It's more like that when it's on. Where is it?
MIT, that's right.
Yes, yeah. I would be shocked if they didn't, to be honest. If there is a sort of vaguely mad science thing, I would assume MIT would have it. So this is sort of more like what it looks like when it's on. We don't want the plasma to touch the walls of the reactor. Plasma will ruin basically anything's day. If you have a nice thing, plasma will probably destroy it. So we use these magnetic fields that they generate with very powerful electromagnets to sort of confine the plasma to a donut-shaped ring around the reactor without touching anything, because you would just ruin the reactor, and you spend a lot of money building that. The other way that they've looked into doing it is with a set of lasers that come at it from all sides, and that's called inertial confinement, where they just bombard it with lasers to keep it in the center, and so that the plasma doesn't ruin everything. So that's kind of the holy grail of energy, of power generation, is fusion. We've been very close to figuring it out for a very long time, because sort of as we learn more, we realize that we don't know that much. And as we get closer, new problems show up. So we don't really know when we're going to figure this out, if ever, because it's really hard to put a sun in a bottle, and just it's very difficult. There's a lot of very smart people working on it, but it is a huge problem. But if we do figure that out, we're kind of set on energy. Yes?
I don't really understand how it's self-sustaining.
The thing that happens with the sun is that you need a lot of the heat and the pressure. That heat generated by the fusion reaction provides a lot of that heat. It's kind of like how a fire provides its own heat once it's going. And the sun is self-sustaining because of the gravity. It keeps all the hydrogen in. That's why we need the magnetic fields to provide that pressure, or the lasers to keep everything focused in there. But as long as you keep the hydrogen there and you keep the bottle holding the plasma away from your machinery, it will kind of keep going on its own. We haven't gotten to that point yet. Our technology is not there. We can make plasma. That's not hard. The problem is that we're trying to get more energy out of it than we're putting in, and that is hard. Because currently, we're basically just dumping energy into it and saying, it's a plasma now, that's cool, but how are we going to get power from it? So that's what they are trying to do with the fusion reaction, is get more out of it than they're putting into it. So that's kind of sort of what are we talking about when we say renewable energy, and sort of where we're going in the future. And that's about all I got. So if anyone has any questions, now is a good time. Yes. Yes. Okay. Yeah. I was taking questions during, so yeah.
2 questions.
What's that?
One. This is a single part question. The other one's.
Uh-oh.
So I've heard some powerful people who theoretically have access to lots of science advisors.
Yes.
Say stuff about clean coal.
Uh-huh.
Is that a thing?
No. No. Coal is coal.
What are they referring to?
Coal is basically coal. If you burn coal, you're gonna get carbon dioxide. That's what's happening. I know there's a lot of regulations and laws in place about what a coal plant is allowed to put out. You are not allowed to just burn coal and put the smoke into the air, because that's really, really dirty. And there's a lot of, so a combustion reaction with just, say, natural gas, which is basically pure methane, that's very clean. That is, you have hydrogen, carbon, and on this side you just have CO2 and water. When you're burning coal, there's all kinds of other things in there. There's like mercury is a problem. There's all kinds of heavy elements that you don't want in the air to have people breathing. You get a lot of very, very dirty ash that's hard to dispose of. So yeah, clean coal is kind of just something made up by people who want to sell coal, if I'm honest. Yes?
So if I'm understanding you, it's clean in the sense of it's only the CO2 that's coming out, which is still an issue, but it's not, the idea is that they're taking out whatever heavy elements.
Yeah, there's basically just coal is coal. Clean coal is like a marketing thing. Having to clean the output of your coal plant that's a thing you have to do regardless. Everyone has to do that, because otherwise it's just a hazard to everybody who lives anywhere near it. So yeah, coal is basically coal. You're not going to escape from that fact that burning coal gives you carbon dioxide. And that's kind of how we got where we are in the first place, is by burning a lot of coal. And like I said, that coal was way underground. It was safe down there. It was fine. And then we put it back in the air. What was the second bit? What was that?
Do you think? No, I want a definitive answer.
Okay.
Is cold fusion actually possible?
Cold fusion?
Yes.
Cold fusion was the term for having fusion at, I believe it was something like, it wasn't cold. It was like 300 or 400 degrees instead of several thousand. But all the indications are that no, that was a thing we tried to do, and it was a lot of hype, basically. And they got very excited about it for a little while, and then people realized, wait, this doesn't make any sense. And then more scientists did very clever science things and said, yeah, no.
You're saying all the science fiction I've ever read is true?
I'm not going to be the one to break your heart, so you have to ask somebody else about that.
Not all of it is not true. but
Okay.
We're not going to tell you which one.
Oh,
Yes,
this was-
exactly. Some of what you may have heard might have been true.
Right.
Can neither confirm nor deny. What else?
I was going to say the future of renewable energy might be more efficient solar and battery storage that will.
Yes, battery storage has been the problem with batteries for a long time now, is that the technology for batteries has not really gotten any better. There have been a couple, working around the edges. They've made batteries a little bit better, but our energy needs have gone through the roof. So batteries have not kept up. There are a lot of, I know at least one or two companies in Cambridge next to MIT that are working on that. There's a lot going on in that field because, like you said, there's a lot to be done there with renewable energy, particularly solar. A lot of types of renewable energy, so most prominently wind and solar because they're very prominent, are not always useful. So if you're in a place that isn't windy, congrats, your big expensive turbine is just sort of nice to look at. That's about it. If there's no sun, you're not going to get a lot of energy out of that. Yes?
Yeah, thanks for giving this talk.
Oh, yeah.
The way you described renewables in the beginning, I actually thought that was the first time I ever heard of it, kind of as like a brain equation. So renewable just means you're using it up slower than you're getting it.
Yeah.
The thing you just said with the energy, not the word you said, but you made this gesture.
Oh, yes.
You made the exponential.
Yes,
like,
exponential.
So that sort of, I know exponentials are unsustainable, but it seems sort of like, okay, so we fixed the problem for a while, we increase the rate for, let's say, wind or something else.
That's sort of why it becomes important to, as any economist or stockbroker or financial advisor will tell you, diversify. We want to be able to get energy from a lot of different places, and there is energy everywhere. Energy is in everything all the time. So things like the wind is always going to be a thing. The tides are always going to be a thing. And that energy is there whether or not we're using it. So we want to look at getting what we can where we can, because yeah, like you said, with exponential stuff like the world population, as more nations start to either develop or electrify, there's just going to be more and more and more demand. And single centralized sources, unless we finally do just put space race money into fusion and finally figure it out after all this time, centralized sources are going to have a really hard time keeping up with the demand. So the idea is to sort of try to spread out the load a bit more, to use what we have where it is. Oh, there are volcanoes here, let's put in a geothermal. You have to make exceptions for things like Yellowstone. It's like we don't want to put things in the middle of Yellowstone. I'm sure there are people who want to, but don't let them make decisions is the important part. But someplace like Iceland, which is, they've sort of looked at what their landscape is like. They've picked what parts of the country they want to preserve from development, and then they've said, okay, here we will put a geothermal plant. And they don't have to be huge, and Iceland's not a big country anyway, so it's fine. And then I don't know what it is, what the situation is in Hawaii. You were there.
I didn't see that.
They hit it very well. Yeah, so any place, I saw that Japan has done it, which doesn't surprise me. They're very future-minded on a lot of tech issues and a lot of energy generation issues. That's that. Anything else? If I don't know, I'll make something up, and it'll sound really good. All right. This has been Breaking Science.
Yeah, thanks for coming,
Thank you.
everyone. Excellent.
Thank you very much.
Very museum of sciencey.
Yes.
I forgot to mention Christian has